Thank you for coming back for the fourth installment. So what did we prove last time? So last time we gave a fairly detailed sketch of the proof of the following result. So if we fix n, that stands for the dimension, and v, that stands for the volume, then the set of all canonical models of that dimension with volume bounded from above by v, so let's say the set of x's such that x is a canonical model of the right dimension with volume of k of x. Since it's a canonical model, then I can just compute this by taking the top self-intersection. I want this to be bounded from above by v. Then this set here is bounded. So more precisely, there exists a projective morphism of varieties of finite type over the complex numbers, such that every one of these canonical models appears maybe non-uniquely as a fiber of this morphism. Right? So you can sort of put them all together in a family. So today's goal, this was last time. So today's goal is to explain how to generalize this result to the case of semi-log canonical models. So for semi-log canonical models, I need to be slightly more precise in the data that I fix. I need to fix, let's say, the dimension, the volume, and also a set of coefficients. And so this typically will be a set of rational numbers between 0 and 1. For technical reasons, maybe at a certain point you also want to think about real numbers in between 0 and 1, which satisfies the descending chain condition. So your typical set is a set of the form 1 minus 1 over k, where k is any integer, possibly infinity. Okay, so we fix these three, and we consider the set, let's call it SLCM for semi-log canonical models, which depends on the dimension, the volume, and the coefficient set. So this is the set of all pairs XB, which are semi-log canonical models of the right dimension, the right volume, and the coefficients of B are actually in this DCC set C, so the right coefficients. Notice that I'm actually fixing that the volume is equal to V, not less or equal to V. So this set here is bounded, by which I mean that we have to show that there's now a pair XB such that we have a projective morphism over a variety of finite type S, such that the fibers of this morphism parameterize this set of semi-log canonical models. Okay, so maybe I should state a few of the corollaries. So the first corollary should be fairly straightforward from the theorem, is that there exists, assuming that we have rational coefficients, of course, there exists well, you can make sense of this even if we're talking about the coefficients being real numbers, but for simplicity, let's assume that they're rational numbers. So there exists an integer m, which only depends on this dimension, volume, and coefficient set, with the property that if we take one of these semi-log canonical pairs, semi-log canonical models with the right volume, dimension, and coefficient set, then mkx plus b is very ample. Okay, so that's the condition that presumably is going to appear in Collat's book to prove that the moduli functor corresponding to these objects is bounded. So that should be a fairly immediate consequence, because after all, we have a family, and we will show that we can assume that kx plus b is itself Q Cartier. So there is an integer m such that this divisor actually becomes Cartier, and then the restriction to every fiber is Cartier. And once you have an ample Cartier divisor of a fixed degree, then the usual Hilbert scheme arguments, just going back to Grothendieck's paper, tell you that this is bounded. So, well, yes. I'm sorry, I take that back. You need a very ample divisor. So you have to, once you know that there's some fixed multiple that is ample, you have to show that there's some fixed multiple that's very ample. So I guess for every fiber, there will be some fixed integer which is very ample, and then you have to observe that it's an open condition. So there's some, by a semi-continuity argument, there's some possibly much bigger m becomes very ample. Or alternatively, you could use some theorems that directly prove that once you have some multiple which is an ample Cartier divisor, sort of Matsuzaka type theorems, that then prove that some fixed multiple is actually very ample. So there's several ways to go around this, but it's fairly direct. One corollary which is not immediate and sort of will be an important part of the proof is the following. So if I look at the set of all possible volumes of kx plus b, such that xb, again, these are semi-log canonical models of the right dimension and the right coefficients. Of course, I'm not fixing the actual volume, otherwise it wouldn't be a very interesting set to look at. So I look at all possible volumes, then this is a DCC set. And so, in particular, it has a minimum, I don't know, little v depending on n and c, which is strictly greater than 0. So every one of these semi-log canonical models in particular has volume greater than some positive constant. And certainly this, at the very minimum, we know from the proof that we saw last time that we definitely need something like this in order to apply induction on the dimension. And I'll show you in a minute exactly where we use them. So one remark.
Why is it a corollary?
Okay, so you missed a couple of words that I said. So let me put it in. It's not an obvious corollary. It's more, okay, so if I were to assume the theorem, it's a lot easier to prove this, but it actually will come as part of the proof of the theorem.
Sorry.
And so.
Because there you fix the volume. Here.
Right. So it will really come out as part of the proof. And as I describe the proof, you'll remember elements from last time, and it hopefully will make more sense. So it's not a direct corollary. The other remark, I wanted to emphasize that what we saw last time was that set of volumes of k of x, where x is canonical model. So it has canonical singularities, then this is discrete. And you may say, well, you're allowing coefficients in a DCC set, so it's not a surprise that the set of all possible volumes is not discrete. Right? Just take P1 and take some interesting boundaries on P1, 3 points with coefficients 1 minus 1 over n, then you get accumulation point from below for volume equals to 1. So clearly, however, if I just look at the set of volumes of k of x with the property that x is, let's say, KLT model. So I haven't formally defined KLT model, but by that I mean that the class of Kx it's a Q-Cartier ample divisor, and it has KOT singularities, then this actually has accumulation points from below. It's still a DCC set, of course, but it actually has accumulation points. Of course, you know, if you want to rephrase this in terms of canonical models, then you have to extract some divisors of discrepancy between -1 and 0, so of coefficient between 0 and 1, and you really get some coefficients that appear that belong to a DCC set. So maybe that's not too surprising, but there are indeed examples where you really do have these accumulation points. And the other remark is, I discussed it previously, but throughout the proof, so let's say in the proof, we may, and hence will, assume that our pairs XB are normal, so they are log, i.e. they are log canonical. The point is that if you have one of these semi-log canonical pairs, you look at the normalization, it breaks up into several components with a boundary reflecting the double locus. And then, so remember that after taking the normalization, we get components yi with boundary bi, and each component will have their volume, and the sum of these volumes will be equal to kx plus b, which I'm fixing to be a fixed amount v. So from this property on the volumes, it immediately follows that, so if I put the sum on i's in I, immediately follows that the cardinality of I is at most this fixed volume divided by the lower bound. Each of these volumes has to be greater or equal to that number. And how can their sum be equal to v? There's a bound on how many of them I can have. And the individual volumes, if I call it capital VI, have finitely many options. And then I wave my hands a bit because there's a recipe of Collard that tells you that you can glue these components back together to obtain the semi-log canonical model. And the data where you glue this together is also bounded. Well, the data itself is bounded. It depends on the double locus. And by adjunction, the double locus is again given by some semi-log canonical model. So one has to think about that a little bit, but it's a technically difficult, but there are no big ideas once you know this theory of Collard. Okay, so let's begin looking at the proof. But before I do that, are there any questions about the statements or from last time? Okay, maybe you'll think of questions from last time because I'm going to sort of go through the proof that we did last time step by step and show you where the difficulties really arise. Essentially, at every single step of the proof, difficulties arise because we're dealing with log pair. Okay, so the first thing you'd like to do, you would like to prove that this set is birationally bounded. Why? Because that's what we did last time. We proved that it was birationally bounded, then we sort of took a resolution of this family that bounded the varieties up to birational equivalence, and then take the relative canonical models to show that it was actually bounded. So it seems like a reasonable thing to do. Now, notice that we have a boundary, so we don't just have to show that the varieties itself are bounded, but the boundaries are also bounded. And so typically when you have a situation in which you have a pair, instead of saying that something is birationally bounded, you say that it's log birationally bounded. And you immediately have a bit of a difficulty even defining this concept, because if you have a birational map, this map may contract some divisors and may extract some divisors. So you have to worry a bit about these divisors that are maybe on X, but not on the birational model, or vice versa. So let me give you what the correct definition of birationally bounded is. So we would like, there exists a pair, let's say Z, D, and a projective morphism let's say F from Z to S, such that for any one of our objects, for any one of our pairs which are semi-log canonical models in dimension n with volume V and coefficients in C, there must exist some point S in S such, let's say, so the first thing you want is that the corresponding fiber is birational to X. So that means that there's a birational map between them. So maybe let's say you need a birational map H sub S from X to Z sub S. So this has to be a birational map. And you want that under this birational map, the support of the push forward of this boundary divisor B union with the exceptional locus for HS inverse, so let's just say for ZS over X, is contained in the support of this divisor D. Okay, so this divisor on Z has to keep track of whatever the push forward of B is on Z. Not only that, but also whatever divisors you have that are exceptional for ZS over X, or whatever divisors that are extracted by this map. Okay, so you need to keep track of these two pieces of information. Any questions on the definition of, yes?
The D, the coefficient of the D, there's no?
No, I'm not requiring, at least yet, anything about the coefficients. I'll get those right later. For now, I'm just comparing the supports. Other questions?
So this exceptional divisor is all the divisors that do not exist on X.
Yes, they are. You know, if I take a common resolution, they exist on some common resolution.
Yeah.
They're not exceptional for this map, but they are exceptional for that map. Other question?
It must be a condition on DS and XB.
DS and XB. So the XB's are semi-log canonical model. Sorry?
With B and DS, what is the relation?
Between B and DS?
Yes.
Oh, it's precisely here. That sort of, so suppose that this map was an isomorphism. Then essentially I'm asking that the support of B is equal to the support of DS.
But there must be a condition about the coefficients.
No, for now I'm not putting any condition on the coefficients.
But aren't you defining log birationally equivalent, or?
No, I didn't say equivalent. I'm just saying it's a step in the right direction.
So this is the definition of log birational.
This is the definition of log birationally bounded that I'm going to use, correct. I mean, the problem is that you can't get the coefficients right unless you really are, in a second, because I also have this issue that at the same time I need to show you that the volumes belong to a DCC set. So in a second I may also drop this volume condition. once I drop that, then if I have one of these zs ds, I can put for coefficients of the d 1 minus 1 over n, all of those. And then it's a mess.
So here you only care about what kind of divisor is showing up.
Yes,
You
yes.
are the coefficient.
And then I'll be careful about the coefficients eventually, yes.
I understand.
Okay. Okay, so that's the definition.
So D, I can think of this one as reduced divisor. for
Yes.
my needs.
Yeah, for the time being, it's a reduced divisor, exactly. And when I have a non-reduced divisor, I'll call it something else, actually. So, okay, so the idea from last time is it suffices to show that some multiple of kx plus b is birational as soon as m is greater or equal to some constant a times kx plus b to the n. So maybe I'll change the statement slightly. I'm going to put a less or equal here. So I'm actually going to show that the ones with volume bounded above by v are birationally bounded. Stronger statement. So that's kind of what we did last time. And so I'm going to show that if I pick an integer, there exist constants a and b, such that if I pick an integer which is greater or equal to a plus this quantity that we saw last time. So this is the volume, and this is the 1 over the nth root of the volume, some fixed positive constant a plus b. As soon as I have m greater or equal to this quantity, I would like to show that the map is birational. The argument we gave last time then the same exact argument shows that x is birationally bounded. Remember, the point is, all you have to, we know that this guy here induces a birational map. So we look at phi m of x, which is contained, take its closure, which is contained in some projective space corresponding to the linear series m kx plus b. And having this kind of estimate automatically gives us an upper bound of the degree of this guy. Remember, it was something like the degree of phi m x bar. Well, that's just the volume of OPN1 restricted to this image. That's going to be bounded from above by the volume of the pullback of this guy on x. But the way this map is induced is from this linear series. So that's bounded from above by the volume of m kx plus b. However, m is of that form, well, we're going to pick, maybe let's call it m0, where m0 is the roundup of this horrible quantity. It has to be an integer, and it has to be greater or equal to that. So the first integer that works is the roundup of this. Well, I don't know. Assume that b was an integer. It doesn't matter if you put it inside or not. So this volume is of the form m0 to the n times the volume of kx plus b. And we're assuming that the volume of kx plus b is bounded from above by v, right? So this is going to be less or equal, just to play it safe, to v to the n. I'm sure you can get slightly better, a plus b plus 1 to the n. And there's no v to the n. Right, this quantity is bounded by v, and this quantity involves, it's something involving 1 over the nth root of the volume plus b to the n. So easy exercise. You just have to collect terms, and it follows immediately. So it follows that, we're assuming that this is birational. It has bounded degree, so it belongs to a bounded family. Okay. The problem is, but y is the boundaries bounded. Oh, that's horrible. Let's say y is it log birationally bounded. Okay, so the problem is what happens to the boundary. Okay, so far what have we done? We've constructed this family Z over S such that for any such X, there's a fiber of this which is birational to X. Now, once you have a family, well, first of all, we may assume that this family is smooth. Of course, in order to achieve this, you have to decompose Z into a bunch of finitely many locally closed subsets, and then where the blow-up process is nice on each fiber. Okay, so let's assume that this family is smooth. Then another thing that is sort of an eyesore is this set of exceptional divisors. Can we just make that go away? Well, our statement is a birational statement, so we don't really care that we actually have log canonical models. We can replace those by any higher model. So we may replace pairs of the form xb by pairs of the form x prime b prime with the property that f from x prime to x is birational. And so to write it in fancy terms, I think I defined this divisor L, so b prime should be greater or equal to the divisor L on x prime, but I doubt that anybody remembers what that is. So what that means is that if I compare kx prime plus b prime, that will, with the pullback of kx plus b, this is equal to some, that difference is some effective exceptional divisor. So E is effective and exceptional. And if this is the case, then that tells me, for example, that the canonical ring has not changed. So in particular, if I do this procedure, x prime b prime is no longer a log canonical model, but it has all the information of its log canonical model. You just take proj of its canonical ring. So you don't lose that information by replacing by a higher model. The volume doesn't change, right? The volume is, so in particular, you also have that the volume of kx plus b is equal to the volume of kx prime plus b prime. So there really doesn't seem to be any downside to this. There's only one risk, and somebody brought it up before, is you got to be careful with what coefficients you pick here, right? Because if you just pick the divisor that's defined by sort of the most natural choice, which would be this Lx prime, that means that I'm picking b prime and e to have no components in common, sort of the most natural thing that you would do. Then, since this is log canonical, it is true that these coefficients will be less or equal to 1, but there's no reason to believe that these coefficients belong to the set C, right? And in fact, there's no expectation that they belong to any DCC set. So if you know this stuff, you know that the minimal log discrepancies are expected to satisfy the ACC. That means the biggest coefficient of this is expected to satisfy the DCC. But it's not true that all discrepancies satisfy this property. It's not true that all coefficients. So in fact, if you just do this, they will not belong to a DCC. There's nothing you can do about it. So we do something much more simple-minded. If we don't like a coefficient, we just increase it and make it equal to 1. So I will define this divisor here. B prime will be equal, I don't know if I had this notation in one of the first lecture, will be equal to m of b. What does this mean? This means that it will be, did I give a name to the map from, okay, I haven't given a name to this one, so I'm allowed to call that one f, I guess. This will be the strict transform of b plus the whole exceptional divisor of f. The exceptional divisor for x prime over x, when I write it like this, I mean everything with coefficient 1, the reduced exceptional divisor. Since this is log canonical, these coefficients will automatically be less or equal to 1, so I can just increase them to 1. By doing that, I'm just making this effective exceptional divisor a bit bigger. I'm not changing the number of sections. So if I make this choice for b prime, then it is obvious that the coefficients of b prime still belong to C. I may have to add the number 1 to this coefficient set. But it's clear if you just add one number, it still satisfies the DCC. So once I make this choice, it's sort of well-behaved from a birational point of view, which, we're trying to prove birational boundedness. Now, the advantage is, once I've made this choice, I can assume that, I call them H sub s. So I can assume that H sub s from X sub s from X to Z sub s is a morphism. And so in particular, when I look at the exceptional divisors for Z sub s over X, this is just empty. There are no exceptional divisors. Watch out that there's a subtlety here that you could be, for different copies of X, you could be blowing up X more and more. The map from X to Z sub S could have more and more exceptional divisors. And that's something that we're going to have to deal with eventually. It's an unpleasant feature. But there's no way of getting around that, because if you have, the most benign pair you can think of, P2 with 4 lines with coefficients 1, you can sort of keep blowing up points of intersection of the line, adding the exceptional divisor with coefficient 1. You go higher and higher. You're not really getting different guys, different semi-log canonical models, but all of those are things that you'll have to consider eventually. And the goal is, in general, to show that all of those blow-ups really are just equivalent. They all, in some sense, really descend to a common model, the same model. So as you can imagine, there'll be some interesting B divisor that will come up in a little while. Okay. So I've done a couple of reductions. I still have not argued that the boundedness of the corresponding divisor on Z automatically follows. So,
Can I ask one?
yes, sir.
So last time when we were proving this boundedness for the general type, somewhere we used the fact that we found this covering family, Z, and we observed that Z is also of general type.
Okay. You're way ahead. That's in a couple of slides.
Oh, I'm sorry.
Yeah, definitely an issue coming up. First, yeah.
Oh.
That was sort of the second step of the proof. We're still at the first step.
Oh.
So.
No, not from this first one. I'm a little worried.
Yeah, you should be worried. It's going to be a major issue, and I'll get to it. But let me set the stage to answer your question. I know exactly what you're going at, and yeah. Okay, we'll get there very soon.
I'll shut up. Yes.
Yeah. Okay, so what we need to do, showing that it's birationally bounded after these reductions, really amount to, we must show that if G is a component of H, S, lower star of B, of the support of this, then the degree of G is bounded. This is certainly a necessary condition. If it belongs to a bounded family, then it must have bounded degree. But it's also a sufficient condition by, sort of Hilbert scheme's argument, I guess Charles scheme argument. By standard. You just look in Grothendieck's paper, it's stated that way. Okay, so how do I show that? Well, what does it even mean? So let's fix, let's say H will be OZ1. So it corresponds to the moving part of this linear series, essentially. So the degree of G is just going to be H to the n minus 1. Well, I restrict it to the fiber S to the n minus 1 and intersect it with G. And my goal is to show that this is bounded from above. Okay. So I want to show that this is bounded from above. So why would that be? Well, so let me start by looking at, I have this divisor B on X, and I want to try and understand the intersection number of B with the pullback of HS to the power of n minus 1. And so this is going to correspond to Kx plus B, the degree of Kx plus B. I'm going to say something very stupid now. Minus the degree of Kx times H upper star of Hs Bn minus 1. All I'm saying is that B is Kx plus B minus Kx. Okay. But now, this quantity here is bounded from above by m0 to the n minus 1, right? Because to make H over S, I used m0 copies of Kx plus B times the volume. So this part is bounded from above. And now, this part here is actually equal to K of Z times hs to the n minus 1. But now this z is like a smooth family over s. It may have many, many components, but it's a smooth family. So this guy here is in a discrete set. So that tells me that this number here is bounded. Okay, but this number here is a sum of bi times the push forward of the corresponding component bi times hs to the n minus 1. So the sum of these degree is bounded from above. But now these coefficients are in a DC set, so they're bounded from below. So I can divide by the minimum of these coefficients. So it follows, the upshot is, okay, so this is greater or equal to bi times g times hs n minus 1. And this bi is bounded from below, so that gives me a bound for this degree of g. So essentially what I'm saying is, once I've shown that the x's are birationally bounded, then the degree of the image of the canonical class is birationally bounded, the whole degree is bounded, and so that gives me a bound on the degree of each component. But I'm definitely already using, well, maybe not that the coefficients are in a DCC, but there's a minimum of these coefficients. Otherwise, they could blow up. Okay, but you shouldn't be sold on the idea that I can do this quite yet, right? Because from last time, we saw what it takes to be able to do this. So what do I mean to be able to do this? I am still trying, I have not made a definitive argument for the fact that I can show that mkx is birationally bounded for m greater or equal to that quantity. The only thing I've shown so far is that if I can get birationally bounded, then I automatically get log birationally bounded. So I still have to argue birationally bounded, right? So if you remember the argument from last time, what we really need is to be able to cut down log canonical centers. Yes?
So is number kz dot hs to the n plus 1 always positive? But it could be negative.
Yes, it's discrete. Sorry?
That is only finitely many.
Yes.
Second term is only finitely many. Because that is flat family.
Right, right. So
Finitely many flat family.
So the emphasis here is on discrete.
But actually finite. This is just finite.
Yes, yes. That's what I meant by discrete, but you're right. That's certainly what I meant, but for some reason I wrote discrete, which is unnecessarily confusing. Yes.
And very small question. So in your first theorem, you allow bi is 0, but not 0.
So every bi which is 0, we just ignore.
Just ignore.
Yeah. So essentially, we are assuming that they're non-zero. Yes, of course. Okay. Oh, okay. So remember in the proof, what we had to do was we produced some non-Kawamata log terminal center, and then we had to cut down its dimension. So in order to be able to cut down its dimension, the kind of thing that we need is we need to be able to control the volume of kx plus b plus d1 restricted to z. So we need to bound this from below by some constant delta, where here z is a non-Kawamata log terminal center of the pair x b plus d1, the Z is in a covering family of X, and if you remember, D1 was linear equivalent to lambda, Q linear equivalent to lambda times Kx plus B, where this lambda is given by a linear function in the volume. I guess in the reciprocal of the nth root of the volume. So that's the kind of thing we need, and now we get to your question. So how did we solve it last time? So if X was a canonical model, so in particular B was empty, then it's of general type. We concluded that Z is of general type. So volume of K of Z is bounded from below by induction on the dimension by some constant little v, which is positive. And then we had this business that Kx plus, there was no B, so just D1 restricted to Z was compared wow to K of Z. So this volume was bounded from below by this quantity, and this volume is the exact thing. You know, it's essentially the same as the volume of Kx restricted to Z, because D1 is a multiple of Kx, and you control how big that multiple is. Okay, so I think this is what you were saying, that this general type case was set up very nicely for induction purposes. Okay, so we're kind of in a bit of good news, bad news situation. So what's the good news, bad news? Well, okay, so let's just assume for simplicity that Kx plus B is ample or big if we're working birationally. Then let's think of the ample case, it's just easier to figure. Then certainly Kx plus B restricted to Z is still ample. And similarly, Kx plus B plus D1 restricted to Z is ample. This is just 1 plus lambda times this. So this is ample if and only if that is ample. So that works very well, right? Now, okay, so that would seem to take care of the first part. How about this part? Well, this is sort of still in the good news, if you're not too careful. Kawamata subadjunction still tells you that, there's a few technical details, but at least in terms of volumes, so we can make this precise, that when I restrict this divisor to Z, it's greater or equal to Kz. In fact, it's greater or equal to Kz plus a boundary. Let's be more precise. Let's say it's sort of, roughly speaking, equal to Kz plus a boundary, let's say delta sub Z, where this is still ample. Right? Because if it's a restriction of ample divisor, it will still be ample. So you may say, great, I'm done. You're not, because you have no control whatsoever on these coefficients. Emphasize no. I mean, the way you're constructing this dz is by taking some very high multiple of Kx plus B, considering the whole linear series, divisors that vanish on something, then dividing by some log canonical threshold. It's a big mess, and this divisor D may have many spurious components with just completely random coefficients. So, and then you still have to do adjunction and see what you get after adjunction. So you have essentially no control over that. So we need to do better.
Excuse me.
Yes?
Is that even not normal?
Yes. And so, in particular, the fact that it's not normal tells you that it's not everywhere a minimal non-Kavamatolog terminal center. In particular, these coefficients could be bigger than 1. They could be anything. They could even be strictly bigger than 1. In fact, if it's not normal, then you sort of automatically know that on the normalization you have some coefficient that's bigger than 1, right? So it's really a mess. So okay, maybe I should tell you the hint why there is some hope. So,
but I thought like a z being singular was avoided. Like the problem was avoided, but just going
the typical picture.
General point. Even if z is singular, you go to a smooth point. So you don't have to worry about the singularity of z, no?
You don't have to worry about it when you're creating the next log canonical center. However, when you're trying to compute this volume, you do have to worry about it. Right? So one option is to go, replace x by a higher model, which is some kind of log resolution. But then you have to be really careful with what you're doing. So here's the idea that
that did not show up in the last argument. Here we do have to worry.
Right, because in the last argument, I just throw this whole thing away. So you may say, oh, can't I throw it away this time too? Well, doesn't seem immediately so, because it's very easy to cook up situations in which these log canonical centers are like P1 or something. So they won't be of general type. They'll have no sections. But the idea is the following. Suppose, so after all, what do you do with a family, with a covering family? You replace it by a birational model where that covering, by a generically finite model, where that covering becomes fibers of a morphism. So suppose, actually, that you're in the situation in which you have a morphism down to, I've used S, let me say T, such that fibers xt are equal to your non-Kavamatolog terminal center. Right? I have not shown you that you can assume that, but suppose that you were able to assume that, then you would have that kx plus b restricted to z is just kz plus b restricted to z. This is ample, and it has the right kind of coefficients. Ample and correct coefficients. Okay. So, and you can completely ignore D in terms of the adjunction. Essentially, D1 will now be a vertical divisor, so it contributes nothing to the adjunction. So that's a bit much to assume. You have to be careful and see what happens when you do some generically finite cover, after which you can assume that you're really talking about fibers. So there is a correction term that you have to consider. And so let me write down what this correction term is. So there's the following theorem. Well, before I tell you what the theorem is, I need to tell you what...
sorry, Chris, I missed it. So you are saying instead of dealing with the original x, you go to some finite cover of x?
Yes.
So that where the non-KLP center
becomes a fiber. So if you remember, that was kind of how we did the proof of this fact that if you have a covering family of a variety of genotype, then each one of them is of genotype. That's the same kind of idea. Okay, so there exists a DCC set C prime depending only on C such that the following theorem holds. So I'll state the theorem, and then I'll be owing you the definition of this DCC set C prime. Okay, theorem. There exists theta, some Q divisor, or depends if I started with real rational coefficients, so let's say an R divisor, on, so I'm calling Z my log canonical center, so on the normalization of Z, such that the coefficients of theta belong to this new, slightly bigger DCC set C prime. The pair Z nu theta is, I probably don't need to say that actually, okay. So then the next thing is, okay, such that Kx plus D1 plus B restricted to Z nu is greater or equal to Kz nu plus theta. So it's something contained in here. That's good, right? Because I need to show that this volume is big. So anything inside that will, with interesting volume will make this volume interesting. And if Z is a general member of a Cambrian family, and let's say Z prime to Z is a resolution, then Kz prime plus M theta will be greater or equal to Kz nu plus Kx. I'll explain everything in a second. It's slightly technical, unluckily. Z prime. And what is this M theta? M theta is the strict transform. So let's call this A. We probably have H already. Mu is mu, the strict transform of theta plus the reduced exceptional divisor. And in particular, Z prime and theta is log canonical. Okay, so sort of take a deep breath and see what I'm saying. Okay, why is this important? So this is important because it tells me that here I have a log canonical pair which compares well to the pullback of an ample divisor on the normalization. So in particular, this says this inequality here, the important thing about this inequality is that it says that Kz prime plus M theta is big. Okay? So by induction on the dimension, then the volume of this guy, Kz prime plus M theta, will be bounded from below by a constant that now depends on the dimension D of Z and on this new coefficient set C prime. Because those are log canonical pairs where K plus the boundary is big, and so my theorem in dimension 1 less gives me a lower bound on their volume. But then you see on the normalization, this is just a push forward of this guy. So the volume of this guy is also bounded from below by this constant. And so this volume is bounded from below by that constant, and I win. Okay, so I have some wiggle room. I need to produce an interesting divisor where I control the coefficients, but that divisor has to be somewhere between kx plus b plus this extra d1 that I used to do adjunction and the original divisor that I'm interested in, which is kx plus b. And you shouldn't be shocked that in the process of doing adjunction, the coefficient set changed. We've already seen very basic examples where you restrict to a line on a cone over a rational curve, and the coefficients change from the set 1 to the set 1 minus 1 over n, to a new DCC set. Moreover, there's something like Kawamata subadjunction going on in here somewhere. So that also will contribute to the change of the coefficients. So now I'll tell you how the coefficients change. And luckily, that's a bit of a mouthful. And then I can show you where this naturally arises, though. Okay, but before, I know this statement is slightly unnatural, so maybe are there any questions? Yes?
I understand, like, this will solve the problem.
Uh-huh.
But we had this problem arising from the Kawamata subadjunction and coming from singularity of z, and why can we do this is a big question.
Okay, so I'm going to explain that now.
Okay.
That is going to be my next step.
Okay.
So that I'll try to explain why we can do this.
Yes.
And I'll try to explain why, essentially, the stupid idea was just to do Kawamata subadjunction for this. You get all kinds of rotten coefficients. Doesn't work. So now I'm going to go on an appropriate resolution, modify this divisor a bit, forget the junk stuff, and what I'm left with will define my theta. That's the idea. And of course, the process of forgetting the junk is not trivial. It uses things from the minimal model program, such as DLT models. So let me try.
What do you do with singularity of z?
I'm actually going to write it down. The quick answer is that whenever you have a codimension 1 point of z, which is singular, you put coefficient 1 there. In theory, it should be greater than 1, the coefficient, right? You put coefficient 1, and it's still going to work. So let's try and see why. Essentially, the contribution of kx plus b, whenever you pass to a generically finite model, is going to be less or equal to 1. Because if you start with something KLT, and you do any generically finite map, it stays KLT. Or sub-KLT, depends if you extract some divisor. So you really, the junk is all in D1, essentially. Okay, so I haven't even told you what this coefficient set C prime is, and I hope I have it written somewhere because it's a bit of a pain, but it's not too bad. So how do you construct C prime? Well, so first of all, you C prime will be equal to the numbers of the form 1 minus t. They have to be in the interval between 0 and 1, such that t arises as a log canonical threshold in dimension d of pairs where the coefficients lie in where the coefficients have the form, okay, let me call it d of c, union possibly 0, where this derived set of c, it's a trivial, it's of the form, it's everything of the form A is of the form 1, let's say n minus 1, m minus 1 over m plus sum of Ci, where Ci's are in C. Okay, so this is a horrible mouthful, but where is this coming from? So I told you that when you do adjunction, it's natural that if you have a cone of a rational curve and you have your log canonical center is one of these lines and you restrict to that, then you will get coefficients 1 minus 1 over m at the vertex, where m is the degree of the rational curve. Now, suppose that you had another line, let's call it B, with some coefficient little c. Well, then the intersection number between these two lines is actually 1 over m. The local index of the singularity is m. So then when you do adjunction, you'll get a plus c over m coming from here. If you had two lines, you'd have a c1 and a c2 over m. So this is the least complicated the new coefficients can be. But now, I am saying that you have to consider log canonical thresholds arising from pairs with these coefficients. And then you have to consider every coefficient of the form 1 minus that log canonical threshold. If you were in a log smooth situation, then these log canonical thresholds would just be 1 minus these coefficients. And so you're doing 1 minus 1 minus, you're just getting the same numbers back. If you're not in a log smooth situation, it's something much different. In particular, it's not clear why this should be a DCC set. So what we need is we need what's known as the ACC for LCT conjecture. So if I'm going to go this way, I actually have to prove that conjecture. And that's what I plan to do next time. And it actually ties in very nicely because turns out that that conjecture is a fairly easy consequence of the boundedness of log canonical models. So it may be surprising, but when I write down, you'll see that.
Wait. You said you were going to use this, but then
Yes. So it's going to be a proof by induction. Actually, to prove the ACC for LCT, I need this boundedness in dimension 1 less. So there's sort of room to spare.
Is this what you were going to talk about in the last lecture?
Yes.
Oh, no.
And actually, that sort of turns out to be simpler than this stuff.
Oh, no.
Okay, so I'm happy to tell you about it another time.
Because I'm going to miss that.
Okay, so this is sort of crazy. Why are these new coefficients arising? Well, it's all built into the way that Kawamata subadjunction works. That's how there's sort of two parts in his subadjunction. One part comes from some modular problem, and the other part comes from the singularities of a certain map, which I'll describe in a second. And these singularities of the map, well, they have to be measured by some measure of singularity, and the measure that is used is the log canonical threshold. So this is sort of forced on you by Kawamata subadjunction. That's what Kawamata subadjunction does. It creates a pair with these kind of coefficients and certain nice properties. Okay, so let's try and define theta. Okay, so I claim that there exists a map of the following form. So we have a map, let's say, from y to x. This is a birational map, a projective birational morphism. Maybe for good luck, y is q factorial. I can write, well, I can always do this. I can always pull back kx plus b plus d1, and I claim that I can write it as ky plus s plus gamma prime, where I want certain properties. So the s, this appears with coefficient 1, and it's not a component of gamma prime. So there is one thing with coefficient 1. And in fact, so S, in fact, is sort of the unique non-Kawamata log terminal place dominating Z. Okay? So as we discussed last time, I can pick the log canonical threshold at the general point of Z, so I can assume that Z, and then I can sort of perturb things a bit, so I can assume that Z is a sort of going to be the unique, has a unique non-Kawamata log terminal place above it, and S corresponds to that unique term. And I'm also going to assume that gamma prime, the coefficients of gamma prime are all greater or equal to 1. Unluckily, there may be many coefficients that are strictly greater than 1, corresponding to points at which this pair is not Kawamata log terminal. Then these necessarily will have coefficient greater than 1. Okay, so why should such a pair exist? It's really non-obvious. It's a consequence of the minimal model program. So what you do is you go to a log resolution, and you would certainly have this kind of thing, except that the coefficients of gamma prime could also be, the only thing that's not achieved by log resolution is that the coefficients of gamma prime could be strictly less than 1. In fact, if you blow up a smooth point of x outside of this boundary, you'll get something of negative coefficient. Then you run a smart minimal model program over the base x that gets rid of all the coefficients which are strictly less than 1. So this is the only similar thing I can tell you for intuition. It's the same exact procedure that, given a surface, provides you the minimal resolution. The same kind of idea. Except that for surfaces, you're sort of just blowing down -1 curves. Here you have to be able to blow down all kind of negative curves with some restrictions. Okay, so what do I have now? Now I'm going to consider, okay, so if I were to do Kawamata subadjunction, how does Kawamata subadjunction work? You have, inside of here you have S, inside of here you have Z. Z is maybe horribly singular, so at least I take the normalization.
Some of the coefficients of B are smaller than 1, right?
I'm going to keep those. Okay, so yeah, so certainly this contains a strict transform of B, f minus 1 lowest star of B. All the new coefficients are greater or equal to 1. Right. Yeah, you're right. Okay, so where was I? If you were doing straight up Kawamata subadjunction, you'd think of it in this way. You can show that on this, you can assume on this resolution, well, if you went to a log resolution, then S would be smooth. On this, you can assume that it's at least normal, and then it will factor through the normalization. And then what Kawamata subadjunction tells you is that you can write, so you can think of Ks, let's say, plus phi prime. This is the restriction of Ky plus S plus gamma prime to S. And this is the pullback of the restriction of Kx plus B plus D1 to, let's say, Z nu. So I'm calling with F, I'm calling everything. This map and this map, just by abuse of notation. So So if I can understand how this guy arises as a pullback from z nu, I can write this restriction. Okay, so the formula to write, so I know that this guy is Q-linear equivalent to the pullback of a divisor on z nu. So we can write this as the pullback of, this is what Kawamata subadjunction tells you, of k z nu plus a boundary divisor, let's call it delta z nu prime because there's a prime there, plus some moduli B divisor, where this is pseudo-effective. And we're sort of going to discard it. It's something pseudo-effective automatically tells you that the volume of the whole thing is greater or equal to the volume of the whole thing when you forget the pseudo-effective divisor. So this is benign. It's the contribution from the moduli problem on some higher model is always an F divisor, so in particular pseudo-effective. This is the divisor that measures the singularities. So the formula for that divisor is for any point P on Z nu, the coefficient of P is computed as follows. You let TP be the log canonical threshold of the pair S phi prime computed with respect to the divisor that you obtain by pulling back P, too many parentheses, the log canonical threshold of this object, and this should be computed over the generic point of P. So if it's a curve, then you just take the log canonical threshold. Okay, so this is what the recipe tells you, and then this delta z nu is the sum of coefficients 1 minus TP times points P. And you can show that these coefficients, all but finally many of these coefficients, these log canonical thresholds equal to 1. So all but finally many of these coefficients are 0. This is a finite sum. And this is the divisor that keeps track of the singularities of this vibration. And it's precisely, if you're familiar with Kodara's formula for an elliptic vibration, the same exact thing happens in that formula. There's some divisor that depends on the singular fiber, and then there's some modular part, which is the pullback, 1 over 12 times the pullback of OP1 via the J function. Okay, so this is the one that I said is not going to work, right? So at first sight, the coefficients are looking not too bad because there are these forms. There are the form 1 minus t. Here's my 1 minus t, where the t's are log canonical thresholds. But now the coefficients of phi prime, well, the coefficients of phi prime, I have to do adjunction. So when I do adjunction, I know that I get this issue of from certain coefficients, I get new coefficients of the form m minus 1 plus sum of ci divided by m. However, these ci's are the coefficients of this gamma prime, and those coefficients include the strict transform of, I should have said also the strict transform of D1. And strict transform of D1 really bothers me because I have no control of that. So I want to do the same exact thing without D1. I'm just going to forget about D1 as much as I can. So to define theta, we're going to pick a smaller divisor, gamma. Gamma will be what? It's going to be the strict transform of B plus all the exceptional divisors for y over x, right? And this is automatically bound less or equal to gamma prime, because what's the difference between these two? Gamma prime also includes the strict transform of D1, and it may include some of these exceptional divisors, it may include them with coefficients strictly greater than 1. Okay, so that's However, the coefficients of this gamma are now in C union. Maybe I have to throw in the number 1 because I'm adding this reduced exceptional divisor. I might as well just assume that C contains the number 1. And then I take Ks plus phi to be Ky plus S plus gamma restricted to S. And I apply Kawamata subadjunction to this guy. I write this as the pullback of Kz nu plus delta Z nu. So no primes anywhere here. Plus this some pseudo-effective divisor. But I don't want to worry about that because it's a not K-trivial vibration. So let me not say that this is equal. I'll define this divisor where delta Z nu is the sum of 1 minus, okay, so maybe I had primes everywhere. I put these T primes. P, where Tp is the log canonical threshold with respect to S, phi with respect to the pullback of P. So, yes?
I have a couple of questions.
Definitely.
So, first of all, gamma prime includes all the exceptional divisors. Is that a requirement?
Yes, yes. So this is how DLT models work. That wherever it's not log canonical, in fact, the coefficients will be even bigger than 1. Okay. The ones less than 1, I get rid of them via minimum model program.
That's number 1. And when you write, like for all P, P is a divisor. Is that what you meant? Yes, certainly, because I'm trying to so this is divisor, a codimension 1 point on Z nu. So it's a prime divisor on Z nu. Codimension 1 place, that's what you meant.
No, point. It actually has to be on Z nu. You can do this in a B divisor form, and it makes sense for places too. But
divisor on Z nu.
Yes, I'm just going to worry about Z nu for now.
Yes.
Yes.
D1 is not be controlled. D1 is not be controlled. And is there any DLT models?
Okay.
The minus case. D1 is not controlled.
D1 is not controlled. So you're worried about the fact that it's not log canonical.
Yeah.
D1 is effective.
It may be sub-log canonical.
But it may be not log canonical.
Okay. But
so think about the case of surfaces. You start with a horribly singular surface. You can still find a minimal desingularization.
But excuse me, I see your DLT program, DLT models, but at that time, and the coefficients is about the effective case. It's not about the minus. It's not included the minus case.
Yes, but I am doing it for an effective divisor, right? I'm doing a DLT model for this object here.
Yeah, but D1 is maybe negative.
No. D1 is an effective divisor.
It's effective.
Yes. D1 is definitely effective. It's the way I constructed D1 was I start with looking at multiples of Kx plus D, sections in there that vanish to a high degree along a point. So D1 is definitely effective. Otherwise, we would have a problem. We'd at least have to assume it's sort of exceptional for some map or something. No, it's definitely effective. So now, you see, since this phi is less or equal to phi prime, it's clear that these log canonical thresholds compare nicely. It's obvious, it's automatic from the definition of log canonical threshold that this pair is less singular, so the measure of singularity is better. This is greater or equal to P prime, and so as a consequence, it's immediate from the definition that delta Z nu is less or equal to delta Z nu prime. And so the definition itself will give me that this condition is satisfied. Right? Because this guy here is, the volume of this guy compares well with Kz nu plus delta Z nu prime. Oh, wow. I should have called this theta, of course, and the other one theta prime. I guess I didn't know where I was going. Yeah. So So by definition, essentially, we set the things up. We consider a less singular pair than this. Now, the next step is not by definition. It involves a bit of work. So I will skip it. But what it involves doing is saying the following. If you do have a general member of a covering family, right, then what that means is that up to a generically finite map, let's call it x tilde, you'll have a morphism to a base, and the general fiber of this base will correspond to the normalization of your z. And then you play exactly this game, but you have to be careful as to how does the log pair change under a birational map, and then look at the restrictions. And so this divisor theta, or delta z, depending how I define it, is sort of built in a way to be very robust from a birational point of view. So if you know Kawamata subadjunction, then you know that this behaves like a B divisor, meaning that if I compute it on any higher model, it pushes back to the right thing. So I'm skipping the details of that. If you're careful when you do this generically finite cover, things will work out. Okay, so you're squinting. You have a question.
Yes, I thought it was okay to stay on X. I do not see the reason why you have to go to X tilde.
Well, certainly if you stay on X, you cannot view these. Maybe there's a way directly on X. I'm not sure. But certainly if I want to think of them as fibers of the morphism, I have to replace X by some generically finite covering.
So you want to do this in a family?
Yes. Right? Because so the first inequality I said always holds. The second inequality, I only know how to prove it when it's a general member of a covering family. Sorry?
I missed how to prove second statement.
Okay, so I haven't proved the second statement. So, and I'm not going to go through the details because you have to keep track of a lot of these log canonical thresholds, how they behave on Z versus how they behave on X and on the resolution and on the finite cover. So I'll have like 4 quantities to compare. It's annoying. However, the main idea is that if you have a covering family, then up to a generically finite map, you can view them as fibers of a morphism. Once you can view them as fiber of a morphism, you can do this argument. Right? If it's a smooth fiber of a morphism, you just restrict. There's nothing interesting going on. However, there are going to be some correction terms coming from the ramification divisor when you do a generically finite cover. So in order to keep track of those correction terms, the best way to do it is to keep track of the corresponding log canonical threshold. Maybe the most convincing argument is, without actually doing the work, is to say that if you have a pair, so this is maybe a fairly well-known fact. So suppose that x tilde to x is generically finite, and we have a map G, then let me write kx tilde plus b tilde is G upper star of kx plus b. Then the pair xb is KLT / log canonical if and only if so is the pair x tilde b tilde. If you don't believe it, try looking at the pullback of dz over z. This is exactly at the log canonical threshold. You have a pole of exactly order 1. And when you do a pullback on the generic finite map, you always get poles of order 1, right? If you increase it, you get poles worse than order 1. and if you decrease it, you get poles better than 1. So what I'm trying to say, if and only if, the same holds for this, KLT log canonical threshold. What I'm trying to say is that this tells you that log canonical thresholds behave well under generically finite maps.
I'm sorry, I'm still lost because you're telling us how to find this theta for a fixed z, yes?
Right. And so for a fixed z, I give you a recipe for a fixed z. And for a fixed z, it always happens that you have this inequality with my recipe.
Okay, so why do I have to go to x tilde?
Because I also need something else. I need this inequality.
So you haven't told us yet.
That's what I was giving you hand waving, but not detailed proof because there's quite a few computations.
That one.
In order to prove this one, you need to go to a generically finite cover. And that's where it's important that I pick the definition that I pick for theta. These log canonical thresholds sort of are built in such a way to behave well on the generically finite maps.
Now I'm happy because I thought I missed something.
No. And details are omited.
No.
I mean, I think everybody's being very patient so far.
The argument did show, if you pick such theta, then I have that inequality.
Right. Yes.
I said, in order to prove that one, you need to go.
You need to do some additional work and keep track of,
I see.
of not just one. You need to keep comparing the two log canonical thresholds.
Now I have.
Okay, so that once you can do that, we have this big thing that we eventually have to prove, which is the ascending chain condition for log canonical threshold conjecture. So, but let's assume that that's in dimension 1 less. So let's assume by induction we know that. Then we're done with what? We're done with showing that the pair that there exists that the pairs are how do you say log birationally bounded. Okay. Now on x, b, we can assume that they are birationally bounded. So here xb, log canonical, kx, the volume of kx plus b is bounded from above by some value v, and the boundaries are in some fixed DCC set C. Okay, now let's see. Do you guys want to take a break? I just realized I've been going for an hour and a half, and raise your hand if you want a break. Okay, so let's take a 10-minute break. It's been going on for a while. Okay, so why aren't we done at this point? Well, the problem is now with the coefficients. Let me try and explain why. So suppose, for example, let's assume that we're trying to show the DCC of volumes, right? So suppose that this property of the volumes being in a DCC set doesn't hold. So suppose we have pairs xi, bi, which are log canonical, the volume is bounded from above, and the coefficients are in a DCC set, such that So how could the volumes fail to be a DCC set? Then I would have to have that volume of KXI plus BI. Okay, let's assume that I have a weakly decreasing sequence. Right, then I want to show that we have the volume that, let's just say we have equality for all sufficiently big integers, right? That's what it means to be DCC, that any non-increasing sequence eventually stabilizes. Okay, so let's simplify the situation, and let's assume, let's also assume that all of these are birational to one of these, a fixed fiber. So suppose that we have morphisms HI from XI to a fixed Z. So this is, of my fancy family, this is just one fiber, such that HI lower star of BI is contained in the support of the divisor D, which again is sort of my fancy D on this one fiber. So I'm not going to worry about the fact that they are birational to Z's in a bounded family. I'm going to pretend that they're actually, that I'm only staring at one particular fiber of this family. If I can't do it for that case, then I can't do it in general, right? Okay, so I've used the simplification I had before, which I've somehow erased, that, you know, I'm allowed to replace the xi's by some resolution as long as I replace the bi by a strict transform plus the full exceptional locus, so I can actually assume that these are morphisms, and then the condition, the log condition, just boils down to the fact that the images of these divisors are contained in this fixed divisor. And we can also assume that the pair ZD has simple normal crossings.
I'm sorry, I have a question.
Definitely.
So in the first statement, the boundedness statement, the volume was fixed.
Right.
But to prove this birationally boundedness, we changed to the volume bounded from above.
Right, because remember, we in order to do the proof by induction, we also need to know at the very minimum that there's a lower bound for the volumes. So we also need to worry about the two problems.
But the final statement is for fixed volume, it's bounded, not
for fixed volume, it's bounded. It's not, in the final statement, it's not true. But you'll see, in the proof of this, you'll actually see where the honest boundedness of the log canonical models is coming from.
Okay, sorry.
Okay, so so now comes something slightly annoying. So let me sort of emphasize, you know, recall that if we have xi prime to xi, some birational morphism, I don't know, nu I, and bi prime is this guy that I'm calling m of bi, which is just the strict transform of bi plus the exceptional set, then the volumes are unchanged. And in fact, the whole log canonical rings are unchanged. So in fact, the log canonical models are unchanged. Okay, so I'm going to consider these objects. So I don't know, I really need sort of to bold them. So I'm going to consider these objects as B divisors. This is a B divisor. What a B divisor means, it simply means that you can sort of compute the coefficient on any divisor over x. If you have a divisor which is exceptional over x, you just pick an x prime where that becomes an honest divisor, and you apply this formula. Right? So all it means is I pick a geometric valuation nu, then the coefficient is the same coefficient as bi if nu is a divisor on xi, and it's 1 if nu is an exceptional divisor over xi. And again, the reason why I want to pick 1 is I cannot put random coefficients. It needs to stay in a DCC set. So once I've done that, then I can define this new B divisor again with the property. So it's going to just be the limit of these B divisors. So what does this mean? This is, there's countably many valuations to worry about, essentially. So what this means is for any valuation nu, this is the limit of okay, so now you may say, this is crazy, the limits don't exist, right? So in order for this to make sense, you have to pass to a subsequence. So for any fixed model z prime over z, there are only finitely many divisors in the support of any MBI considered as a divisor on Z prime. Why is that? Well, this is certainly contained in the strict transform of D, let's just call it D tilde, plus the exceptional locus. So now, these numbers belong to a DCC set. So passing to a subsequence, you may assume that it's a non-decreasing sequence, so it's tending to a limit, namely the sup of those. So on any finite model, this is a non-issue. And if you have a countable sequence of divisors that you're interested, you do some kind of diagonalization argument to make sense of this limit. So maybe that's a little less believable, but certainly what's believable, what's immediately clear is that we can define, for example, phi to be the limit of these divisors on Z. So this divisor on Z is would just be HI lower star of BI. And this limit, we call it phi, is certainly less or equal to this reduced divisor D. Each individual divisor is less or equal to that. Question? Okay. So it's going to get a bit ugly. There's nothing I can do about it because, again, this is the kind of picture you have. You have a simple normal crossing divisor with coefficient 1 and 1. You can blow up along this point as many times as you want and get a whole collection of divisors in between, which will also appear, you'd expect, with coefficient 1, but you're allowed to consider pairs where the coefficients are anywhere in C, so you can put, starting with coefficients 1 and 1 here, you could have 1 minus 1 over K1, 1 minus 1 over KT, and so on. You can create all kinds of crazy things, and they will all belong to this sort of countable set of pairs that I have to consider, and I have to make sure that their volumes are well behaved, right? And it's possible that when I blow up and I decrease this coefficient a bit, it's possible that I get something of smaller volume, that I chip away at the volume. So it looks kind of like the odds are stacked against you, right? If you have something of volume, say 1, with two things of coefficient 1, you say, well, let me just blow up this point of intersection here, and let me put a smaller coefficient than it should be. Instead of putting 1 on the strict transform, I'll put 1 minus 1/2. The volume will have dropped, and can't I just continue doing this over and over? Well, somehow the fact that these coefficients are in a DCC is telling you that this procedure of chopping down the volume has to terminate. But the whole crux of the matter is that there are infinitely many divisors to worry about. All the divisors, all the toric valuations that live over this point could possibly create an issue. If you were only extracting one divisor, chopping down the volume would correspond to putting a smaller coefficient. With the coefficients are in a DCC set, you can't keep decreasing these coefficients indefinitely. I'm proving nothing. I'm just trying to give you an intuition that there really is a tough difficulty here. There really are, you start from your favorite pair with positive volume, you blow up a point, and you can see a way to cut down the volume a bit, just by replacing the exception divisor that should have coefficient 1 with some coefficient like 1 minus a third or something. Okay, so
what's wrong with this? Sorry, you were saying.
I'm saying that if you start thinking about it, you may despair.
So we cannot keep decreasing the volume.
Yes. Okay. So
why is that?
So if there were only if you only blow up once, so it's pretty clear that the only interesting thing to do is to blow up this singularity here. If you only blow up once, you only get one new divisor. If you put 1, you get the same volume. So what are your options? You could put 1 minus 1 over k here. This may decrease your volume. So let's say I put 5/6, and that decreased my volume. Then I say, okay, I'm trying to look for a counterexample, right? So I'm going to put a smaller coefficient and decrease the volume even further. I'll put 3/4, and then 2/3. But my coefficients are in a DCC set. I can't repeat this procedure infinitely many times. So the next thing I could do is say, okay, well, I run out of options with this divisor. Let me blow up another point and play the same game. And then another point, and then another point. But you see, okay, eventually I'll have to start doing an actual proof, and I can give you a pretty good idea of this proof. But you see, if I put coefficients like 5/6 here, when I blow up this point, I also get coefficient 5/6 there naturally. So when I want to decrease the volume, I have to pick a smaller coefficient in my DCC set, regardless of what valuation I'm looking at. That's the intuition. Now, writing an actual proof is a pain. So Alexeyev did this in dimension 2, where, roughly speaking, it's exactly what I said. You only have, in high dimension, you have all kinds of strata, codimensional strata. So it is kind of the same thing, but you have to get much better at bookkeeping, essentially. Let me try and give you a much better idea of why this is going to hold. Even though that I guess that is the main idea. It would be great if I could find find my notes. Here we go. So let me show you the first easy case. So if phi, this divisor that I've defined on Z, so if the pair Z phi, in fact, is terminal, then in fact the volume of kxi plus bi is equal to the volume of kz plus phi, and in fact I should say the canonical rings are the same. Why is that? So again, these coefficients are in a DCC. So when I look at any particular one of them, eventually they are non-decreasing. So in fact, I can, so that tells me, since this is the limit, and these are eventually non-decreasing, I know that Z, comma, hi lower star of bi, that these coefficients are going to be less or equal to these coefficients. So this is also terminal for any sufficiently big I. So now, what does it being terminal mean? That tells me that if I look at kxi plus bi, that will be of the form hi upper star of kz plus hi lower star of bi plus some exceptional divisor ei, which is effective and exceptional. Why is that? Well, okay, the difference between this and this is clearly exceptional because this is the push forward of that. Why is it effective? Well, you see, the definition of terminal is that when I pull back this, the only stuff with positive coefficient that I get is the strict transform of bi. So clearly, this is bigger than the strict transform of bi, of the push forward of itself, by sort of definition of the push forward. So this is automatic once you have terminal. Okay, so now what do I have? Well, I have, let me look at the volume of kxi plus bi. That's the same as the volume of kz plus hi lower star of bi. But now, the coefficients of the bi's on this fixed model are eventually increasing, right? So this is going to be less or equal to hi lower star hi plus 1 lower star of bi plus 1 for every sufficiently big I, just by virtue that the coefficients are in a DCC set. So if these coefficients are bigger, it's automatic that the volume, right, the difference is effective, so automatically the volume will be possibly bigger. And since this guy is also terminal, that's the same as the volume of kxi plus 1 plus bi plus 1. But I had assumed that the volumes were non-increasing, and now I have the volumes are non-decreasing, so this means that the volumes are the same. Volume kxi plus bi eventually constant. And I'm happy. Okay. But actually, I've done a lot more. Because now you see, not only this is true for the volumes, but this is also true for the canonical rings. Right? So now, proj of kxi plus bi is also isomorphic to proj of kz plus hi lower star of bi. And I claim that these, we have finitely many possible of these log canonical models. So let me at least write down the general theorem that guarantees this. So this would be telling me that at least for that one fixed fiber, I have finitely many possible log canonical models. So I have to borrow a theorem from the minimal model program. And the theorem is the following. Let Z B1, I don't want to use B, D1 be a KLT pair. And let's say with simple normal crossings for simplicity. Let's let D2 be a divisor which is smaller than D1 such that K Z plus D2 is big. Okay, so in particular, if this is a KLT pair, then KZ plus D2 is also KLT. And the same is true for any intermediate divisor. Any intermediate divisor will be KLT and will be big. So then, so this is borrowed from BCHM. Then there exist finitely many birational maps the I from Z to WI such that for any intermediate R divisor between D1 and D2, so I should say that these depend on a finite set I equals 1 through n, this is dimension m, such that for any intermediate divisor, there exists I between 1 and m with Phi, let's say, Wi is the log canonical model, so Wi is proj of the log canonical ring K Z plus D. And even if D is an R divisor, you can make sense of this. I don't want to worry about that. It just means that you can write it as an R linear combination of, as a convex linear combination of Q divisors, and for each of those Q divisors, the honest proj is the same thing. There's a way of making it sense. This is proven by a compactness argument, so you have to be able to do things with R divisors. And it's technically annoying, but it's not actually difficult. So if you are on some compact set where you have both KLT and big conditions, then you can find there are only finitely many log canonical models to worry about. So once you've reduced the problem from these abstract pairs XIBI that could be all over the place to the fixed model Z, then this theorem sort of immediately tells you that there are finitely many of these. Why is that? Well, I've assumed that this is terminal, so all of these are bounded by a KLT divisor, in fact, by a terminal divisor. And I have to argue that they're all greater or equal to some big pair, but you see the coefficients are non-decreasing, so just pick one of the pairs, then for sufficiently big I, all the pairs are greater or equal to that, and so any one is something of general type, so they're all greater or equal to that fixed one of general type. This is sort of tailor-made to apply. So essentially we apply it with D1 equals phi and D2 will be HI log star of BI for some sufficiently big I. That's how you apply it directly. Okay, so the next step will be to say something about why is it reasonable to assume it's terminal, right? I mean, terminal is pretty far from where the problems are happening, right? So you may say, you completely cheated, right? Because here the interesting thing was the least terminal point, right? But I'll get to that in a second. Any questions about this part of the proof? Okay, so if you believe that, then you sort of work up your courage. Step 2, well, not step 2. Let's say, suppose Z phi is KLT, right? So the typical KLT example is, you know, you have two guys, 1 minus epsilon, 1 minus epsilon. Wow, this is not very intimidating because I tried to convince you earlier that I was free to replace Z by a higher model and X by a higher model. So in this picture here, so okay, let me explain what to do in this picture and then I'll write the words. So what you would do is you blow up this point in common and you'd get something, the natural coefficient to put here is 1 minus 2 epsilon. That's just what you get by doing the pullback formula. And you see now that things have slightly improved. It's getting closer to be terminal. For example, if epsilon were 1/2, then this coefficient is 0 and it's already terminal. After finally many blow-ups like this, you will get disjoint divisors, like with coefficient 1 minus epsilon, 0, 1 minus k epsilon, 0, and so on. Right? You can, at any point, the quantity, the sum of these two guys minus 1 keeps decreasing. So after finally many steps, it will be less or equal to 0. So what that means is we can pick a finite sequence of blow-ups along strata, let me write it this way, of M phi. What do I mean by this? Strata of phi and of its, you know, you have to do it many, many times, so you have to consider phi and its strict transform union the exceptional set. That's what I'm using this M to denote, this thing that keeps track of the strict transform of phi and the exceptional set. So you keep blowing up along the natural strata that you get so that you get a birational map from, let's say, Z prime to Z, where K Z prime plus phi prime is equal to the pullback of Kz plus phi. Phi prime is some effective divisor, and Z prime phi prime is terminal. And this really is, I don't know, if I had some example where it's like 3/4 and 3/4, I blow up once at the risk. So you'll be bored by this very soon, and so you'll give up that it's sort of an obvious thing. So the next thing I get is coefficient 1/2, right? Because if you just blow this up, the corresponding coefficient is 3/4 plus 3/4 minus 1, which is 1/2. So now you blow up those points of intersection, you get new exceptional divisors with coefficients now 1/4 and 1/4. And okay, technically this is canonical, not terminal. So you blow up once again along this point here, and you'll get coefficient 1, 3/4, 0, 1/4, 1/2, 1/4, 0, and 3/4. And in higher dimensions, you can prove this by induction on the dimension of each strata. It's not pleasant, but it's not hard. It's very straightforward. Okay, but I told you that the statements are robust from a birational point of view. So I am free to replace z phi by z prime phi prime, and now I'm back to the terminal case. So in that case, I'm happy. So where does the interesting stuff happen? Well, the interesting stuff happens if this phi is actually log canonical. Yes.
I'm a little bit worried
Uh-huh.
because you blew up z phi, and our assumption was xi to z was a morphism.
Right.
So
But
when you blow up, you have to blow up xi again.
I'm just going to put coefficient 1, and that does not change the log canonical model, and it does not change the volume.
And that is taking the MBI, that by that you define phi. So in this process, you're actually
Okay.
constantly changing phi. So if you tell me it doesn't change phi, then I'm happy.
Okay, so I have to prove to you.
That's okay.
No. Okay, this is fine. I mean,
You can tell me that.
let me prove it. Let me prove it.
No, just.
I mean, you caught me. I swept something under the rug, and so let me prove it.
No, sorry about that.
No. I mean, the one time I'm trying to sweep something under the rug. Okay, so Kenji says, sure, I'm allowed to do whatever I want. I can replace z prime by phi prime, but what am I going to use for the xi? Am I going to get the right coefficient along this exceptional divisor? Because the coefficient of phi prime, it should be defined in terms of the new coefficients of the BIs. Okay, so this is how it works. So you can just assume that the xi, in fact, maps to the z prime, which maps down to z. Right? And what you're saying is that I have that possibly phi prime, the way I've defined it, it's not clear. It may actually not be the same as the limit of the m bi z prime. So what I need to do now is I need to change the BIs so that this happens. And I need to show you that by changing the BIs, I'm not affecting the volumes or the canonical rings.
Okay, you can say that can be done.
Yeah, but it's actually kind of interesting to see. I mean, it's an easy thing, but it makes you a bit more of a believer that this is, and I'm kind of essentially using it in the next step anyhow. So what happens here? What happened is that what we're going to do is we change bi prime will be sort of the minimum between the coefficient of phi prime and b. So not looking at my notes, so I'll do the computation in a second, but if I had to guess, it would be the minimum, since this is a morphism, so bi prime at the divisor nu, so nu is a divisor on z prime, I would put this to be the minimum between this guy here and phi prime. So the minimum quantity between these two. Now, why is this a reasonable thing to do? Because, you see, the point is that the volume of K xi plus bi is actually equal to the volume of kxi plus bi. And now I'm going to decrease this by considering the minimum between this and the divisor that I get by doing the natural sort of log pullback of hi lower star of bi. So what I'm saying is I'm allowed to decrease this divisor for any divisor that lives on xi, in particular this divisor nu. I'm allowed to decrease it anywhere between its original value and the value that I get sort of by pushing forward b and pulling it back. Now you see hi, I'll explain this in a second. Hi lower star of bi is going to be less or equal to phi because that's how phi is defined as the limit of the push forward of these bi's. And consequently, this guy here is less or equal to L of phi, which happens to be phi prime. So why do I have this sort of semi-surprising thing? Well, the point is that sections of any multiple of kxi plus bi, I can think of them as naturally being included in sections of any multiple of kz plus the push forward of bi. If I have a section in here, I push it forward, then I get a section in there. But now, by what we've done about 10 times, this is essentially by definition of L equal to these sections here. So this is telling me I have, this is, inside of this guy, I have this, okay, so this contains H0 of m kxi plus, for this bi prime, bi prime. So when I read this, what do I say? Well, the sections in here are naturally in here, and hence naturally vanish on the difference between these two guys. In other words, these sections only have, they're allowed to have poles along bi, they only have poles along here. So the poles of these sections are not the whole of bi, they're sort of somewhat redundant poles. The redundant poles are exactly what I'm throwing away. Right? By this, maybe you don't even need to worry about this. By this inclusion, I know that these sections automatically only have poles along this. Hence, they are sections in here. That's all I'm saying. It's not a deep fact, but when you have to keep track of, one of the problems is that you have infinitely many pairs and infinitely many divisors to worry about, and then you construct a B divisor, and it's very sort of hard to keep track of everything, and typically B divisors don't descend. But for example, when you have a terminal model, then that's one example in which you can get them to descend easily.
Thank you.
Okay, so then let me just mumble 2 words about the log canonical case, and then we'll be done for today. So suppose that Z phi now is honestly just log canonical, but not KLT, then what you want to do is you want to sort of proceed by induction on the smallest non-KLT center. Well, I'm not going to worry about writing down an induction, but the typical situation is, again, you have 2 guys of coefficient 1 in your phi, and you're worrying about what happens over that point. And there's 2 possibilities. So suppose that this divisor D is greater or equal to L of Z phi. Then you have nothing to worry about, because that means that So, okay, I need to do some limiting procedure, which I'm not going to worry about. But what this means is that when I'm looking at my xi bi, this d is essentially the limit of these bi's. So I can assume that these bi's are sort of greater or equal to 1 minus epsilon d. Right? D is their limit, so they get arbitrarily close. And these are sort of greater or equal. So then this forces them to be, in particular, they'll be greater or equal to LZ HI lower star of BI, maybe times 1 minus epsilon. Let's not worry about that. But then that tells you precisely that this is the case where there is no problem. That tells you that the volume of KXI plus BI is actually equal to the volume of ZHI lower star of BI. And so your problem is now a problem on a fixed variety, and you're in good shape. So the problem is precisely when this limit, there is some valuation for which this limit is less than that quantity. So if, on the other hand, d nu is strictly less than LZ phi for some nu, okay, so in particular, this is a positive quantity. So that tells you that it's a toric valuation. So this nu is a toric valuation. The importance of being a toric valuation, what it means is, like in this picture, what it's saying is precisely the only issue is that divisors that you obtain by blowing up this point repeatedly. Okay? So you can sort of solve the problem by blowing up that point repeatedly, or by taking a toric blow-up, depending on your preference. I would prefer to look at the toric blow-up. It's mildly singular, but it can be controlled very easily. So we let what do we z nu to z be the corresponding toric blow-up. And we do the trick that I just explained before that tells me that we are going to we're going to replace, now we have to define phi nu, the divisor on z nu. This will be given by mu minus 1 lower star of phi, the strict transform of phi, plus there's one exceptional divisor which will appear with coefficient d nu. So this is the coefficient times this one exceptional divisor corresponding to this toric blow-up. And similarly, you have to do the same trick for the xi's. So you can assume that the xi map to both of these guys. So you replace the bi prime will be bi will be, so the multiplicity of bi prime along evaluation, I don't know, alpha will be the same thing, a bi if alpha is different from nu, but it will be, do I just want to take d? I think I can just take the same value. It will just be d nu if alpha is equal to nu. So by the same computation I did before, it's not going to change the volumes of these xi's bi. But now there is some coefficient that should have been 1, which is actually now less than 1. So what I've done is I started from this situation with coefficients 1 and 1. I've now blown up a point and replaced this by coefficient d of nu, which is strictly less than 1. I have improved the situation somewhat. Now, again, there are two cases. One case is when the nice equality holds, in which case I win. One case is when we have a bad inequality, in which case there's another distinguished divisor that I can blow up. So I will get another extraction. So here I have coefficient d nu. Here I have another coefficient d nu 2, let's say. And you do the computation to check that this coefficient will be smaller than the coefficient d nu. And you keep repeating. But now, these coefficients actually belong to the closure of your DCC set C, which is also a DCC set. And so this procedure eventually stops. And then the final word of warning is that, is there a final word of warning? Yes. That I have slightly cheated. This coefficient d nu, it's not clear that it's in the coefficient set C. How does this coefficient d nu typically look like? It looks like if you started with two coefficients, it looks like something like the typical form of this coefficient is of the form sum of 1. These coefficients are always of the form a fixed linear function depending on the blow up of your original coefficients. So you have to apply some fixed linear function. There's finitely many rational coefficients that you have to apply to this DCC set. So you get a slightly distorted DCC set. But it's easy to see that it's, again, a fixed DCC set. That's being slightly swept under the rug. But maybe I'll stop here. I'm out of time. It's been 2.5 hours. So thank you for your patience. I'll stop.
Sorry, Chris.
No. That I have finitely many families.
Yeah.
I've sort of almost proved it because I've shown you that if you have
It's birationally bounded. You proved it.
right.
And then fiber-wise, there is no strictly decreasing sequence of volumes.
But I've also shown you that whenever you can descend everything to a fixed model, then you actually have finitely many families.
Each this. Say it again?
So the trick for showing the DCC of these volumes
Yes.
is, for example, in the terminal case, to show that you only really care about their image on Z or on some finitely many blow-ups of Z. Okay? So whenever you can do that, the finiteness of models is then clear because you just take proj of that guy.
Okay. Finiteness models.
Right, you have to use this BCHM theorem that tells you if you have finitely many, so if you have two divisors, both KLT and big, any divisor in between corresponds to finitely many log canonical model. So the only real issue about, the thing that you have to be slightly careful is the log canonical case. Because that theorem is clearly going to fail in the log canonical case. You would need to have finiteness of log canonical models even as you go to the log canonical boundary. You would need to know abundance to prove that.
But that's okay. But it's suppose, like I showed, for each Z, there are only finitely many log canonical models.
Right.
Okay. Then?
Now you need to do it for the whole family.
Yes.
So you need to apply something like deformation invariance of Perugina. Right, to be able to do log canonical models in a family. It's a non-trivial step. The key to that step is this deformation invariance of Perugina that tells you that you can sort of fit log canonical models together in a family.
So you're not done yet.
I'm not done yet. I'm not done yet. I am done. I'm essentially done for one fixed fiber.
Yeah, yes.
Without having really proven all the details of the finiteness of models, you should believe finiteness of models as long as they are epsilon KLT for some fixed epsilon.
Okay.
That's all we've done.
Are you going to do this in the next lecture?
So in the next lecture, I will say a couple of words about the deformation, but unluckily it relies on Hsu's deformation invariance of genera for non-general type case. We are not able to eliminate that non-algebraic part of the proof. So I'll spend probably maybe half an hour discussing this, not more than that, and then I'll give a proof of the ACC for log canonical thresholds using the theorem. That's the big thing that's left. So that's the plan for next time. Any other questions? Again, if you come up with questions later, don't hesitate to send me an email, drop by the office, or hunt me down some way or another. Thank you.